Okay, so implicit differentiation. I'm going to go ahead and start by assuming that you have seen all the kinds of differentiation tactics. Specifically, you know how to differentiate polynomials, you know how to differentiate exponentials, specifically exponentials base e, so like y equals e to the x. You should also know how to integrate trig or differentiate, sorry, trig functions like y equals sine of x, cosine of x, all that fun stuff. Okay, those are generally the first kinds of derivatives that you learn, and then you start learning techniques for tackling complex derivatives. So you should also have learned, as far as techniques are concerned, you should have learned the product rule. And so let me go ahead and just write that down really quickly. That is, if you have two functions that are multiplying, you want to take their derivative. It's the derivative of the first times the second plus the first times the derivative of the second. You should have also learned the quotient rule. And all of these are important to talk about implicit differentiation. Quotient rule is just f over g prime is equal to f prime g minus fg prime all over that denominator squared. You should, oops, there's a t on quotient. You should also have learned the chain rule. And that's going to be imperative to know to be able to do implicit differentiation. The chain rule basically says that if I'm taking the derivative of a function, let's say y is a function of t, where t is another function of x, then dy dx is equal to, first I will take the derivative of y with respect to its independent variable t times the derivative of t with respect to its independent variable, which is x. And you can see here, algebraically, a lot of people see this as, oh, you can cancel the dt's and you get dy over dx. Technically speaking, mathematically, that's not true, but I'm not certain if your instructor knows that or not, but it's actually not true that you can cancel those dt's. But visually, it works out. So anyhow, now I'm going to step back for a moment and just ask you to think about the following. The derivative with respect to x of, let's say, the sine of x. Now, you should know that that turns into the cosine, but I'm actually going to be a little more complex about this. I'm going to say, yes, it's true that the derivative with respect to x of the sine of, we'll put a little question mark there, is equal to the cosine of whatever that question mark is. But then, following the chain rule, you would hop inside that sine function. Let me go ahead and just highlight what I'm talking about. You hop inside this sine function here, and you would take the derivative of whatever that variable is with respect to x. So times the derivative of that variable with respect to x. In this case, really that variable is just an x. We started with an x, so there's really no need to go through this process, but it's important to see what this means. So that would be the cosine of x times the derivative of x with respect to x. Well, that's just 1. dx over dx is just 1. So this turns into the cosine of x. And you can do this all day long with any function you want to take the derivative of. The derivative with respect to x of, let's say, something squared minus something to the first plus 3. Well, that's going to equal, if I just consider this as a chain rule, it's going to be 2 times that something to the first power, right? And then you have to hop inside and take the derivative of that something with respect to x, minus the derivative of that something with respect to x, plus the derivative of 3 with respect to x. And of course, the derivative of a constant is a 0, but I'm being sort of long-winded here. And so this will be 2 times, well, let's suppose for a moment all those question marks are actually x's. So it's x squared minus x plus 3. And that would be 2 times x to the first times the derivative of x with respect to x minus the derivative of x with respect to x plus 0, because we know the derivative of a constant is 0. Those dx's are 1, right? So this will be just 2x minus 1 if it were x squared minus x plus 3. And a lot of people don't think of it this way because, well, taking the derivative with respect to x of x squared minus x plus 3 is so simple to you because you know the tricks. It's 2x minus 1. But what if I were to change things up here and say that's the derivative with respect to x of y squared minus y plus 3? This actually doesn't change if you remember my arguments when they were question marks. So when these are question marks, we're going to treat this case as if it was just a bunch of question marks. So if you take the derivative of that, it'll be, let's see, the derivative of something squared is 2 times that something to the first power times the derivative of that something with respect to x, minus the derivative of the next term, which is the derivative of something with respect to x, plus the derivative of the next term, which is the derivative of 3 with respect to x. In this case, because we don't know what y is, that dy dx is just going to hang out there for a while. We don't know what it is, so we just have to write dy dx. The 3 is a constant, so it just disappears. But that's what that derivative would be because we just don't know what y is, so we can't say dy dx is 17 or pi or anything like that. Now let's continue forward. You want to do implicit differentiation. Suppose for a moment that I told you that the quantity x squared plus y squared squared is equal to 3xy. And I wanted to find dy dx. In this case, I would go ahead and take the derivative of both sides with respect to x. So I will apply to both sides. Let me just write it so you can see it in a different color. I'll apply the derivative with respect to x to both sides. So the left-hand side will be the derivative with respect to x of this ugly statement, x squared plus y squared squared. The right-hand side will be the derivative of, with respect to x, of 3x y. So again, think in terms of pictures. On the left-hand side, I'm taking the derivative with respect to x of who knows what. In fact, I'm going to highlight that. I'm going to say whatever I'm highlighting here, I don't know what it is, which we actually don't. Okay? But it's something squared. And what's the derivative of anything squared? Well, that's 2 times that something to the first power. That's something I'm going to go ahead and highlight here. We have 2 times something to the first power. That something I'll fill in. It's just x squared plus y squared. However, then you have to multiply it by, just like we have been doing every time we take a derivative, like the derivative of y squared here, we wrote as 2 times y, and then we took the derivative of the inside of that, which was just the derivative of y. In this case, we're going to take, we've already taken the derivative of something squared. That something happened to be an x squared plus y squared. Now we're going to multiply that by the derivative with respect to x of the inside, which is x squared plus y squared. And we'll get to that in a moment. Actually, maybe I should finish. Well, no, we'll get to that in a moment. Yeah, maybe we should finish this out. Okay, the left-hand side, let's go ahead and finish it out. We have 2 times the quantity x squared plus y squared, all being to the first power there. And we're multiplying it by a statement here. It's a summation, so I can split that derivative. It's a derivative with respect to x of x squared plus the derivative with respect to x of y squared. That's what you can do. Properties of differentiation allow us to split summations or differences. And to continue forward, we have that 2 times the quantity x squared plus y squared. And we're multiplying it by, well, the derivative of x squared, derivative of anything squared, is 2 times that something to the first power. And then you would hop inside and take the derivative of that something with respect to x. Of course, that's just a 1, and normally I would not expect any of my students to write that, but it's important when you're learning implicit differentiation to see that really, when you take derivatives, you're going all the way down to the x, or the interior function, if you will. Plus the derivative of something squared. Remember, the derivative of something squared is 2 times that something to the first power times the derivative of that something. Now, just cleaning up that left-hand side, I have 2 times the quantity x squared plus y squared, and I'm left with 2x plus 2y times dy dx. And a lot of people like to write that as y prime, but I'm going to leave it as dy dx for the moment. Let's see this action on the right-hand side of the equation. We have a derivative of 3 times xy. First of all, properties of differentiation, I can factor that 3 out. So it's 3 times the derivative with respect to x of xy. And also note, this is a product rule. It's a product of two different functions. So the product rule tells us that this will be the derivative with respect to x of the first function times the second, plus the first function times the derivative with respect to x of the second function. Well, let's see. That dx there is a 1, so this just becomes 3 times the quantity 1y plus x times dy dx, because again, we don't know what dy dx is. And now what you would do is, this is completely actually cleaned up. This is going to be 3y plus 3x dy dx. And now what you would do is you would isolate dy dx using some algebra here. So I would move things around and whatnot. But I have to go to class to teach. But that's the idea of implicit differentiation. I know that it was kind of quick because I only had a few minutes to do it, but that's really the basics behind implicit differentiation. I could do a lot more with this because there's a lot more that you can learn about implicit differentiation. But this will give you the basic skills initially. What you want to remember is whenever you're faced with a derivative of anything, really, the derivative with respect to x of e to the x squared or something like that, you really want to think of that as, listen, that's like a derivative with respect to x of e to the junk. What's the derivative of e to a power? Well, that's just e to that power times the derivative with respect to x of whatever that power was. Let me fill in this stuff. The junk here was x squared, so e to the x squared times the derivative with respect to x of x squared. And of course, that's a squaring function, so we have to know its derivative technically is just 2x, but I'm going to be, again, somewhat wordy about it. That's e to the x squared times the derivative of junk squared is 2 times that junk to the first power times the derivative with respect to x of that junk. What's playing the role of the junk in this problem at this point is x itself. X was being squared. So all those words that say junk there will just say x. So we'll have e to the x squared times 2x dx dx, which is just 1. So cleaned up, this will be 2x e to the x squared. Okay, now I'm off to class.